Hi, I'm Sean,
I'm Chang.
and welcome to Software for Science.
So, Sean, what were you going to talk about today?
We're going to use windowing to scale machine learning models to larger data sets than we could otherwise have done.
Last time, we have this Numpy as strided. I remember that you're like, don't ever do this, don't do that. Like your computer was like screaming at you, and but it sounds like we're going to use that for windowing today. What are the relationship between using that function called strided and what we're going to do today, which is windowing?
So actually, mm, that function helps us to perform the windowing ourselves. And the reason they get so fussy about it is because it's just very raw, direct access to NumPy's internal structures. That's all there really is to it. There's no guardrail.
When you say no guardrail, what are some like bad thing that could happen?
So the most obvious thing is that you can access data outside of the allocated memory for that array. So it's quite possible that you would ask for a stride that's longer than the whole matrix, and then you end up the first item worked out just fine, and then the second item ends up like pages and pages later off in the program's memory, and it may be a region of memory that you're not allowed to access. It becomes very messy and difficult to debug, mostly because sometimes it's areas you are allowed to access, and sometimes it just has garbage, and sometimes it has zeros, and so you'll end up doing all kinds of havoc. I mean, just imagine if like you ask somebody to go clean your house or something, but they did it blindfolded, like who knows what could be missing or rearranged, and you don't want to do that.
So that's the reason they put on all those warnings. And last time you mentioned something about segfault. Is that what it is?
So segfault is just your kernel's punishment for you accessing data that you were not allowed to. So when you allocate memory, there's a region of memory that you are allowed to use, set, modify, however you please. But you're not just allowed to access any memory you can address because some of it's not yours. Um, and so with these strided situations, you can end up accessing memory that you didn't allocate, that's not yours. And so a segfault is simply when you try to access somebody else's memory or somewhere you're not allowed to, then all of a sudden your program gets killed. And it's very unceremonious. Like that instruction is the end. There's nothing else happens at that point. You're just toast. So that's what makes it very difficult to debug because you might still access your own memory by accident, just not the memory you allocated. And in that case, actually nothing. It might be, and quite frequently, nothing goes wrong. And you don't actually even see it most of the time. And then, lo and behold, your program randomly segfaults, and you didn't change anything, and you're like, how did that even happen, right? I didn't. I look in my git blame or whatever, nothing changed, and then it segfaults, right? And you're thinking, why? Well, that's because there was just some random chance that that other space you accessed wasn't something that you owned. So then it crashed.
In using the windowing function, how would you replace the for loop? Like what we're going to do in terms of code, in terms of our code today.
It's actually pretty simple. So where normally I would have created an entire matrix before, because we're planning on putting it into a scikit-learn model or something like that, I would have allocated the whole matrix and then placed one row at a time into that matrix. But instead, we simply want to take the original vector and then wrap it in a funny way. And so we'll just turn maybe 2 or 3 lines into one line. So to show how you would use NumPy windows, we're going to go through 3 steps of so first we'll create a sample dataset, then we'll convert it into windows, and then after that we'll actually train a model on it and show the results. So first, let's create some sample data. We need to decide a couple things, such as the number of samples we want, the width of the window, and the size datum involved. We have to choose the size datum because strides actually give us byte level control, and we don't want to show up in the middle of any particular data. So we wouldn't want to have just the last 4 bytes or first 4 bytes or 2 bytes or something of an 8-byte double precision floating point. So let's say that the length is 200, the window size is maybe 10, and then the depth, we'll say, or the size of one datum is 8 bytes. Okay, so now let's set up some noise, and now let's add them together. Okay, this is nearly no fun at this point, so we would really rather see something. Okay, so at this point we can see a kind of noisy sine wave, which is pretty much what we want to have. Okay, now if we give it a few more examples, maybe we'll get a slightly better result. No, that's not exactly it. I want it to span a couple waves, so there we go. Get about 3 cycles. Okay, so now let's break this up into windows. So to do this, we'll set up Windows is np lib stride tricks as strided. Okay, now it's going to give us a whole lot more tips here than we really need. So let's just say the input here is line in. Okay, and we really just need to fill in 2 things: shape, I'll fill that in, and strides, which I'll fill that in as well. And hopefully it won't give us too much annoying help. For shape, we need to decide the number of windows we want by the size of that window. So the number of windows we want is a little bit trickier than you might expect. It's actually the length minus the width of one window plus 1. This is always the case for windows. If you want it to begin and end and all be valid. There's a problem that you can't actually center a window on the ends, or because in the end they would be sampling, or part of that window would be outside of your original sample data, and not only is that numerically inaccurate, it's actually kind of dangerous in the sense that it could cause your program to crash because you might read data outside of what you've allocated. Okay, so the second dimension here, of course, is always the width of the window. Now I'm going to line these up in kind of a meaningful way. Hopefully you don't find it too annoying, but you'll see that the strides actually relate to each shape. There really isn't a stride for the outermost shape, but the next one is actually going to show you the distance between each particular window, which in a normal world would be W times D. And then we want one more, which is actually relating to the size of each particular datum, or the stride between each datum, and that, of course, we already defined as D. But in this world, we actually want the windows only to be offset from each other by 1 data point, so they actually overlap. And that's why the trick of this whole thing is actually to comment out, or to remove, W times, and only get D. Okay? So that is what gets you windows. Now plot, of course, won't work now on Windows because these are actually multiple, so it's a matrix instead. So we can actually still show that. What we'll do is IM show on Windows. And it's pretty, it's pretty clear what we'll come up with that. And it's kind of inconveniently tall. So let's reduce the size the number of samples for a moment so that we can get an idea. Yeah, here you go. You can see there's this kind of diagonal stripe. And that's because there's the wave that we're kind of sliding across, and each one of these windows is one further on that wave. Okay, great. So now let's actually break it up into training and testing data. So this is not the perfect way to do this. Don't exactly copy and paste, but when you actually do this yourself, you should make sure to avoid that half of the window is in your training data and half in your test data, because then you'll actually be testing, at least in a small portion, on your training data. So here's what it would look like, though, in the trivial case where we're not too worried about that. So we're just going to take the first 20% and place that in test. So I'll take windows up to L divide 5, and then windows from L divide 5 on. Okay, so that much was easy, but now we need to do some training and testing on it. So for that, I'll pick out something from scikit-learn. Let's go with an SGD regressor. So we'll say model equals SGD regressor, and we'll fit it on train. Now here, it's a little bit more interesting. We need to make sure that we leave a little bit for the model to actually train on. So this means that we're going to take all of the rows, but all the columns up to the last one. And so now let's train again with still all the rows and only the last column as the predicted variable. Now, if we predict on that model and we give it the testing data up to, well, all of the rows and up to the last, then this will be the estimate. Okay. Now, what's important to realize is that you're actually testing the last element of every window. So I want to show the result, but it's going to be a little bit more complicated than you probably expect. So let's do pyplot, and we'll plot just the estimate here, and I'll label it estimate. Okay, that's going to be completely uninteresting, but at least it will bring up a dialog. Okay, so you can see that looks vaguely signy. Okay, so let's pick out what the actual signal in that place would have been. So we'll do signal, and then we'll label it signal. Okay, and now it'll just pop out to you exactly what's wrong with this. Okay, you see that it's actually shifted over a little. So we actually want to see the signal starting at one less than the window width. Okay. Oh, did I make a mistake? This is still not looking that great. I wonder what it would have done at just W. Ooh, yuck. Well, it looks like that was right. It just didn't fit all that well, I guess. So now let's give the actual line in as well. Okay, so I'll do from W minus 1 on, and we'll label that line in. Okay. And there you go. So that's what this would look like. Might be a little bit, maybe a little nicer to only see the area we've predicted. So there you go.
We've seen the code, and it's working. When should we use it, and what are some of your thoughts of how our audience may be able to use it?
Whenever you're using as strided, because there are no guardrails, you need to pretty well understand what your code is doing. You should probably even maybe work out the math a little bit yourself to make sure that everything is kosher. In fact, I feel reasonably sure that there's some generic solution here, and I've spent a number of days actually trying to write functions that will enforce security constraints on these windowing functions, so that hopefully I can keep from crashing my applications that way. And I have yet to find anything that was completely airtight. There's a lot of little niche cases, and I'll give an example that people often forget for convolution, and that it's only valid in the middle of the picture. So like you can't actually take a window and end up with the same number of windows as you had elements before, because you can't get it right to the edges. And if you're doing that in 7 dimensions at once, it rapidly becomes confusing. And so that's why I kind of recommend that you should probably do this in your end user software or in some models or something where you are the one that wrote it and probably are also maintaining it. But when you do it in a library, just be very careful with that, because it's a source of untold havoc if it happens to break. And it's very, very difficult for someone who didn't write it to understand how some of these errors are even possible. So just keep that in mind. If it's your own software, do what you want. But if you're going to give it to somebody else, just be really careful, or maybe even just accept a little bit more inefficiency and go the long route instead.
Thanks for watching. If you like this video, please press the subscribe button, and we will see you next time.